Welcome. In this video, we're going to show there exists a number whose cube is one more than the number itself, and we're going to use that with the intermediate value theorem. So let's just name our number. Let's say our number is x. Now, I don't have to find an actual numerical value for x. I just have to show that it exists, that it's out there. And now, what does the cube of this number look like? Well, that's x cubed, and I want to show that its cube is, so that means is equal. When you see is, think equal sign. I want to show that this number cubed is equal to 1 more than the number. Now, I can rewrite this as x cubed minus x minus 1 equals 0. And I'm going to take this one step further. I'm going to name this. I'm going to name this polynomial g of x. Now, so long as I can show that g of x equals 0 somewhere, and that can be anywhere, then I have shown that there's a number that's 1 more than its cube. And now, in order to show this, after we verify certain conditions, which I will get to shortly, I just need to find two places, and actually I don't even need to draw the y-axis for this. This is the x-axis. I need to find one place, A, where g of A is less than 0, and then another spot, say B, where g of B is greater than 0. And then based on what we know from the intermediate value theorem, in order to connect these dots, without lifting my pencil, I'm going to have to cross the x-axis somewhere, and that's what I want to show exists. I want to show that this value c exists here, such that g of c is equal to 0. Okay, so let's double check that we have the conditions met to use the intermediate value theorem. Now, g of x is a polynomial, so it is continuous on the real numbers, and in case you're rusty, that's negative infinity to positive infinity. Now, I don't know what numbers to test, so just looking at this, I'm going to put in a 0 for x, because if I try a 0, I know that I'll just get negative 1. So let's try g of 0. G evaluated at 0 is equal to 0 cubed minus 0 minus 1 is equal to negative 1. All right, that tells me that g of 0 is less than 0, and that's this point here that I was interested in. Okay, so next let's try a different value. Let's try 1, and again, it's because that makes the arithmetic easy. I have 1 minus 1. All right, so for our next point, let's try 2. And I decided to skip 1 because I can see already if I do 1 cubed minus 1 minus 1, I'm going to end up with 1 minus 1 minus 1. I'm going to end up with negative 1, which doesn't help me because remember, I need g of 0 not to equal g of whatever other value. So g of A cannot equal g of B. And if I choose 1, positive 1, they will equal the same value. So let's try 2. G evaluated at 2 is equal to 2 cubed minus 2 minus 1 is equal to 8 minus 3 is 5. So g of 2 is greater than 0. Okay, so now I know that b equals 2 and a is 0. So somewhere between 0 and 2, I am going to show that there is a root. So let's just reiterate one thing. We know g is a polynomial, so it's continuous on R. So g is certainly continuous on the closed interval from 0 to 2. Since I have a continuous function on a closed interval, so that when I evaluate this function at the endpoints of the interval, these values are not equal to each other, I can apply the intermediate value theorem. So based on the intermediate value theorem, so I know that 0 lies between -1, and 5. So, by the intermediate value theorem, which I am abbreviating as IVT, there must exist some value x equals c, and this is in the closed interval from 0 to 2, such that g of c is equal to 0. Since g of c is equal to 0, it follows that c cubed minus c minus 1 equals 0. Hence, c cubed equals c plus 1. So this number c is precisely the number we were looking for. C cubed is equal to 1c plus 1. C cubed is equal to c plus 1. That is, c is a number so that its cube is 1 more than the number itself. And we are done. I hope this video was helpful.